and I actually pulled some of the questions from the United States Chemistry Olympiads. So they are kind of difficult questions. But I think we should go over it. So question one is a little bit tricky because sulfur and phosphorus are both exceptions to the octet rule. So you can see the answer. You can see the answer here I posted online. So for number two, so which statements about the fulminate ion are correct? Okay. So everyone read the handout I posted, right? So I don't know if everyone saw this, but I posted a new handout, a review of lesson 3 on new ways to make Lewis structures, an algorithm that might be easier for you. So CNO minus, and then minus. Okay. So remember the first step was to determine the total number of electrons. Can someone tell me how many valence electrons are here in this ion? The total number of valence electrons. So let me check that. So 6, 12. Yeah, right, 16. So how did you get that number? So we get 4 from carbon, we have 5 from nitrogen, and 6 from oxygen. And then since we have a minus charge, we have to add another electron, +1, so this gives us 16 electrons. Does that make sense? Okay. So we have 16 electrons to work with. So let's start putting in our bonds. So let's start with putting in a nitrogen. So how many bonds does oxygen usually like to form? An ideal case. Does anyone remember? Right. So oxygen will usually form a total of 2 bonds. We can put that in. And now nitrogen likes to form 3 bonds, right? So we can put in another bond here. But now carbon doesn't have enough bonds, so we'll just put in another one for now. Okay? So this is what we're working with for now. So can someone tell me how many electrons we've used to form the bonds? How many electrons are in those bonds? So if each bond has 2 electrons, right? Great, we have 8 electrons because each bond has 2 electrons, and we have 1, 2, 3, 4 bonds. So now we have 16 electrons minus 8 electrons. We have 8 electrons left to add in lone pairs. So we use these lone pairs to complete our octets. So can someone tell me how many lone pairs we should put on this oxygen atom? So remember, each lone pair is 2 electrons. So we need to add 4 electrons to this oxygen, so we add 2 lone pairs. All right. So now we have, so we've used 4 electrons, so we have 4 electrons left, so we'll just put them on carbon. Okay, so here's one resonance structure. So now to check if it's right, we have to check our formal charges. So can someone tell me what the formal charges are on the 3 atoms? So does everyone remember how to calculate formal charge? Okay. So Okay, so can someone tell me what the formal charges are? Or tell me if you want me to go over it. Okay, great. So -2 and +1. So we get this by splitting all the bonds in half and sharing we distribute the electrons in the bond, and then we compare that to the amount of electrons that the neutral atom would have. Okay, so we have this 2- charge, which is very unfavorable. So this resonance structure is not so good. So to create new resonance structures, we can move around the double bonds and the lone pairs. So does anyone have a suggestion on how to create a better resonance structure? So you can just unmute your microphone if you have a suggestion. So we want to minimize the formal charges. So how can we do that? Okay, well, this carbon is very negative, right? And carbon is not very electronegative, so that's not so good. This oxygen is fairly electronegative though. So we can move some of the negative charge onto the oxygen atom. So let's move this double bond onto the oxygen atom. So now we have this. Right. And then +2. But now this nitrogen has an incomplete octet. So how do we solve this? Well, we can move some of the electrons on the carbon to form a triple bond, which we will draw as this arrow. So C N O +1 -1 -1, and the whole thing is negative, right? Does everyone agree with this Lewis structure? Does everyone see how we got this? Okay. So now, oh, and I forgot to draw a lone pair. I forgot to draw the lone pairs. So sometimes I might not draw the lone pairs, and that's my bad, because they're not technically required. They're not technically required, but at this stage, it's probably better if you include them. So now, looking at this structure, you can answer the question. So the nitrogen does have a positive formal charge, but it does not have a lone pair of electrons, so the answer is 1 only. Okay, so this very interestingly named heterocycle with this structure. So give the hybridization and geometry for every non-hydrogen atom. So the arsenic, the carbon, and the carbons. So let me go back. And there's a lone pair. Okay. So did everyone read the handout on VSEPR? Oh, there should be a hydrogen. Did everyone read the handout on VSEPR? Okay, so let me pull up the document. Okay. So remember that the steric number is equal to the number of lone pairs and bonds, where we count double bonds and triple bonds as a single bond. So, can someone tell me the steric number for all of these atoms? So ignore the hydrogens for now. We don't need to care about their steric number is obviously just 1. So can someone tell me the steric number for all of these atoms? Okay, let's start with carbon. So carbon has this bond, and this bond, and we count the double bond as 1 bond. So this means we have a steric number of 3. Okay, now let's look at this and you can make the same argument for all the other carbons. Now, we have this arsenic atom. So we have 1 bond, another bond, and a lone pair, So this means we have a steric number of 4. Okay? So now what? So with the steric number in mind, we can determine what's called the electronic geometry. So this you can think about is like how are the electrons arranged around that atom? So how are the bonds and the lone pairs arranged around the atom? So let's start with carbon because it doesn't have any lone pairs, so it's a bit easier. So we have the steric number of 3. Does anyone remember what the geometry should be? So imagine we have a point, and then it has 3 other points around it. And these points all repel each other. So they will all want to repel each other, so in an arrangement like this. And Angelo is right, this is called the trigonal planar arrangement, where each bond angle is approximately 120 degrees, depending on the characteristics of that molecule. So yeah, so the electronic geometry of this carbon atom is trigonal planar. But also, we don't need to consider lone pairs since there are no lone pairs. So this one also has a molecular geometry of trigonal planar. So this is trigonal planar. So all of the other carbon atoms are like this. Does that make sense? So all of the carbon atoms are trigonal planar. Okay. So now let's move on to the arsenic. What's the electronic geometry of arsenic? So if we have 4 things that all repel each other, what shape should it be? And you can review, you can look at the hand, you can refer to the handout. All right, so we also need to consider the lone pair though. So when we consider the lone pair, what's the overall geometry for a steric number of 4? So it's just tetrahedral. So I'll draw a tetrahedron, right? Does everyone kind of see how this is a tetrahedron? So what's a tetrahedron shaped like? So we have a triangular base, and then they all converge to 1 point, right? And this is in the back. I don't know if it's the best drawing. Basically, the point is that, so you can look up a picture of a tetrahedron if you want to later. tetrahedron. So this bond angle is going to be about 109.5. Okay. So now we have our four substituents. We have our four things bonded to the connected to the arsenic. So we have a lone pair, a hydrogen atom, a carbon atom, and a carbon atom. So let's fill those in. So carbon, put the carbon here, carbon there, and hydrogen here. And then over here, we have a lone pair. So I'll draw it like this. So, yeah. So, as you might have noticed, this kind of looks like a pyramid. And it has a triangular base. So we call it trigonal pyramidal, like Answov said. So this is a trigonal pyramid. So now let's try to do a perspective drawing of this. So let me see if I can do a drawing of this. Chemistry does require some art skills. So let's see. So imagine we have a plane. So this is our plane. And then you can imagine like the z-axis here. And I'll let this be the y and this can be the x. Okay? So we have our plane. So what our molecule should look like is this. Right. So it should look something like this. So all of these atoms are in the same plane. So carbon, 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 carbon. So these hydrogens are all in the same plane because those carbons are trigonal planar. However, this arsenic is going to be pyramidal, so the hydrogen atom will come out of the plane. Okay. So the hydrogen atom bonded to arsenic comes out of the plane, and we have a lone pair. Okay. So this is going to be our molecule shape. So feel free to draw that or something. I don't know. Okay. Oh. Okay. In which molecule are there two distinct sets of sulfur-fluorine bond lengths? So I will spare you the hassle of drawing these Lewis structures because they do break the octet rule, but I'll just draw them for you. Nope. The lone pair here. So S. Oh, my bad. This should be a lone pair. It's a lone pair. So these are the Lewis structures. Okay. And what I do want you to notice is that the formal charge on sulfur is 0 in all of these cases. So with the idea of minimizing formal charge, that might help you try to create these structures. So what I want you to notice is that, okay, so in these two bonds are equivalent, right? Because like imagine I label one of them F1 and F2, and then I switch them. F1 and F2. This is the same thing as this, right? These are the same because I can always just rotate this. I can always just rotate the molecule, right? So these two are the same, okay? These two positions are the same. And the same goes for this one. And then for this one, you can imagine that these are all the points of an octahedron. So these are also all equivalent. So these bond lengths will all be equivalent. Here is a little different, right? So let's see. For this atom is 90 degrees away from this one and 90 degrees away from this one. So it's quite close to these two atoms. And the same goes for this atom. So this atom is also 90 degrees away and 90 degrees away, okay? However, and it's 120 degrees away from this one. However, this one is different because it's 90 degrees to both of these and 90, but it's 180 degrees from here. So this one's a bit different. And of course, this one also is 90 degrees away from the lone pair, while these ones are 120 degrees away from the lone pair. So these two positions are different, okay? And you can imagine like, so if we draw a plane, I think the best way to imagine it is like you have a lone pair and two fluorines in the plane, and then coming out of the plane, you have two more fluorines. Right, and you have two more, and then these two are coming out of the plane. So you can imagine like this is almost like a globe. If you imagine it to be a globe, do you imagine if I were to draw a globe around here? So you can pretend this is the Earth. Then this is the axis. These are the poles. This is the axis, and these points are on the equator. So we call these positions equatorial, and this one is axial. So I hope that clears up confusion regarding that. Okay. Okay. So now let's talk about sigma and pi bonds. Someone had a question about this. So first of all, let's look at a simple molecule. So let me think. Let's just do C2H4. Oh. Okay. So can someone tell me the molecular geometries? Can someone tell me the molecular geometry of carbon? Okay. So what's the steric number? Can someone tell me the steric number? 3, right? Because this double bond we consider to be a single bond. So then the structure is what corresponds to a steric number of 3? So it's trigonal planar, right? So it's a trigonal planar structure. And can someone tell me the hybridization associated with the trigonal planar structure? So remember, if you saw the Vesper handout, so hybridization. So what's the hybridization? Great, sp2. So we combine. So let me draw my orbitals. So this is an s orbital, so 2s. And we have 3 2p orbitals. So I should probably draw it like this. So I'll draw it like this to emphasize that the s orbitals are lower in energy. So for carbon at least, we can draw it like this. Okay? So we just move this electron to here, so we get this. You can move that electron to here. This is just one way of visualizing. I don't know how well it works for you guys. So now we combine these orbitals to form a set of new orbitals called the sp2 orbitals. So we'll call these sp2. And then we have a 1p orbital. Okay? So basically we just combine 2 p orbitals and 1 s orbital to get these new hybrid orbitals. And the shapes of these new hybrid orbitals are like this. So you have one big lobe and then a little lobe. And then if you arrange these around the atom, it looks a little something like this. Okay. So these are our 3 sp2 orbitals. Okay. So now we're ready to draw our bonding diagram. So all of the carbon and hydrogen atoms are in the same plane. And our sp2 orbitals are also in the plane. So we can draw them like this. That's awful, but it's okay. Right? Okay. Can someone tell me what kind of orbital we have on hydrogen? So what's the outermost electron on hydrogen? There's only one. Right? Okay, so yeah, it's an s orbital. It's the 1s orbital. So I'll just draw that as a sphere here. Okay? Great. So now each of these have one electron. And each of these also has one electron. So these 2 electrons will pair up to form a bond. Great. So now we have our bonds. Oh, I should probably do that in a different color. Great. Okay, so what about this p orbital here? What about that p orbital here? So that p orbital comes out of the plane, kind of like this. And it also has one electron. Okay. So there can be a bonding interaction between these 2 p orbitals. Because when orbitals overlap, there's a bond, okay? So this is how bonding happens, or orbitals overlap. Okay? So if you notice, in this bond, so if I draw the carbon-carbon bond, these carbons are on this line, which I will call the bonding axis. And the orbital overlap is on the bonding axis. So this orbital overlap is in the area of the bonding axis. So we call this a sigma bond. But for the p orbitals, they extend above and below the bonding axis. So their region of overlap is not on the bonding axis. So we call these pi bonds. So this is where we get the whole S and P, the sigma and pi bond thing, okay? So a handy trick to remember is that, so let's say we have atoms A and B and they have a double bond. So this double bond corresponds to 1 sigma and 1 pi bond, usually. And then if we have A triple bonded to B, this is 1 sigma and 2 pi bonds. And then if we have A single bonded to B, this is just 1 sigma bond. So you can just remember this if this is all too confusing for you. Okay. Let me see if there's anything else I wanted to go over in the homework. Okay, great. So, and if you have further questions, you can ask me. Okay. So now let's look at our topic today, the big topic today, which is stoichiometry. So let me try something. Let me make sure this works. Oh. Okay. So stoichiometry. So stoichiometry is all about how do we turn all of this theory into like practical meaning. So how do I talk about grams of sodium chloride or moles of ammonia? How do I say like how much stuff is here? So how do I look at a pile? How do I look at something and say how much stuff is here and how much of it will react to form this amount of stuff? So this is kind of math heavy, so you should probably get a calculator if you don't already have one. So, or use your phone. Okay. So I want to make sure everyone has a calculator. So stoichiometry. So the first important topic I want to talk about is dimensional analysis. So converting between units. So how do we convert our units? We use what are called conversion factors. These are ratios equal to 1. So because they're equal to 1, so 1 is the multiplicative identity, so we can just, so it won't change anything. All it does is change the unit. So these are just ratios that are equal to 1. For example, there are 5,280 feet in a mile. So this ratio is equal to 1. There are 5,280 feet per mile. And there are, that should say seconds. I'm not sure why it says minutes. So there are 3,600 seconds in an hour. So we can say there's 1 hour per 3,600 seconds. So then, as an example, how would we convert yards to feet? So we know that there are 3 feet in a yard. So we multiply 3 yards by the ratio 3 feet per yard, and the yards cancel out, and we get 9 feet. Right? So, yeah. So just use conversion factors. It's not too tricky. So, metric prefixes. So does anyone recognize any of these prefixes? Yep, good, great. So some of these are common and some of these are not so common. And the ones that you really should know are giga, mega, kilo, deca, deci, centi, milli, micro, nano, and maybe pico. Right. So looking at this chart, so how many tons of TNT are in a megaton of TNT, for example? So look at the chart. So how many tons of TNT are in a megaton of TNT? $1 million, right? So you can just use scientific notation. So 1 million equals 10 to the 6th equals 10 to the 6th, which equals 10e6. So these are all acceptable ways of writing that, but you should probably use the exponential notation. The e is usually on calculators, okay? So for, let's say an example. How many nanograms are in 1 gram? Right, great. So 10 to the 9th. So we can do this by saying, okay, so a nanogram is equal to 1 billionth of a gram. So there are a billion nanograms in a gram, right? You can do the math. Okay, so let's do some problems based on these. So you might need to look some of the conversion factors up, but I'll just give you 5 minutes to do these conversions. So the first one, convert 2 meters per second to kilometers per hour. And if you have a numerical answer, just post it in the chat. I also have to do these calculations, so give me a minute. Point 2, yep, that's correct. So just keep on moving to the next one, Swiley. So 2 meters per second. So there are 1,000 meters in a kilometer. So we multiply that by the ratio 1 kilometer per 1,000 meters. And notice that the meters cancel out. And then times 3,600 seconds per hour. So this cancels out. So you get 7.2. And then for this one, sometimes you might need to use multiple conversion factors. So in this case, we do 3 times 10 to the 8 meters per second times 10 to the 9th nanometers per meter. So the meters cancel out. Now we do times 3,600 seconds per hour. So the seconds cancel out. Now 24 hours in a day. So the hours cancel out. And 365.25 days in a year. And the 0.25 is because of leap years. So you have to add an extra day every 4 years. So we add 0.25. So then this gives us 9.47 times 10 to the 24th nanometers per year. So that's how many nanometers light will travel in a year. So that's basically how long a light year is in nanometers. Great. So I think everyone understands how to do them. I want to introduce the concept of a mole. So here I have a picture. So 2 moles per liter, right? Okay. So moles are not, in chemistry, moles are not animals, but they're the central unit of measurement. So everything revolves around the idea of the mole. So 1 mole is defined to be 6.022 times 10 to the 23rd units of something. So I want you to all write this number down. This number is very important, and eventually you will probably memorize it. So 6.022 times 10 to the 23rd units of something. As an example, 1 mole of H2O molecules is equal to 6.022 times 10 to the 23rd atoms of H2O. I mean molecules of H2O. That should say molecules, not atoms. Molecules of H2O. So what is this number? 6.022 times 10 to the 23rd. So this number is called Avogadro's number. So Avogadro was a chemist from the 1800s. And Avogadro's number is usually abbreviated as N with a subscript A. So capital N with subscript A. And that should be lowercase. So a lowercase n. So can I just add this? So yeah, so ignore that. So n is equal to the number of moles. So if you see like n in an equation or something like that, it often means the number of moles. So a lot of people get confused by the idea of a mole. So remember, the word mole is kind of like the word dozen. So instead of saying, oh, I have a dozen eggs, you can say I have a mole of eggs. So when I say I have a dozen eggs, that means I have 12 eggs. If I say I have a mole of eggs, that means I have 6.022 times 10 to the 23rd power eggs. Okay, so this is a huge number because atoms are very small. So it has to be a huge number. So here are some problems. So how many formula units are in 4 moles of Na3PO4? Okay. So can someone tell me how many formula units are here? So how many things of this are there? So when I say I have 4 dozen eggs, I have 4 times 12 eggs. So in this case, I have 4 moles of Na3PO4. So that means I should have 4 times Avogadro's number formula units. So the answer is 4 times Avogadro number, the Avogadro number. So how many moles of sodium ions are there? So each formula unit has 3 sodium ions, all right? So each formula unit has 3 sodium ions. So that means if I have 4 moles of this, I have 4 times 3. So I have 12 moles of sodium ions. So, and how can we can actually even do this using conversion ratios. So if I have 4, so then I have, so for every mole of sodium phosphate, I have moles of sodium. So if I want to convert 4 moles of Na3PO4, all I have to do is this. And the moles cancel out. Okay. So let's go back to the presentation. Okay, so here's, so can someone just do the last 2 questions? So if we have 12 moles of sodium ions, how many sodium ions are there? Yeah, so 12 times 6.022 times 10 to the 23rd. So, and if you want, we can do this in terms of conversion units, conversion factors. So why not? So 1 mole. So we know that there are 6. I'll just abbreviate as Na. So Na. So how do you? So this is Avogadro's number, not sodium. So what's the difference? So I've written the N in cursive to make it clear, and it's a subscript. Okay. So I hope that's clear. So Na. So we have Avogadro's number, units of something, per mole. Right? So if we have 12 moles, so this is an important definition that you should know. So if we have 12 moles, we simply multiply by this conversion ratio divided by mole. So in this case, the units of stuff is atoms of sodium. Okay? So as one final question, just to make sure everyone understands what the mole really means. So let's say you became a trillionaire or something like that, and you bought 1 mole of eggs. So how many 1 dozen egg crates could you make from your 1 mole of eggs? So someone can just like, you don't have to actually do the calculation, just like type the calculation in the chat. Like, what would you do? How would you do this calculation? Yeah, so 6.022 times 10 to the 23rd divided by 12. Right, great. So I don't think that needs to be explained right now. Okay. So why would it change? Okay. Okay. So why have we chosen this seemingly arbitrary Avogadro's number? Well, the reason why is because it helps us relate what are called atomic weights, remember the very first lecture, to grams. So this atomic weight, so this number on the bottom part of the element symbol is called the atomic weight. So that's like how much does that atom weigh in atomic mass units. So where is it? Okay. So what are called atomic mass units. Or AMU for short. So what is the key conversion factor that you need to know here? Well, oh, no. Okay, so 1 mole of atomic mass units equals 1 gram. So can everyone write that down? Okay. So what is the atomic mass unit? Well, I won't go into the definition really, because the definition is, for some reason, complicated, but you can just say that the atomic mass unit is about the mass of a proton. Slash neutron. These protons and neutrons weigh about the same. So, can someone tell me how much a proton weighs? And put the number in the chat, please, so I can check it. So what is the mass of a proton in grams? Right. So a proton is 1 AMU, and then we multiply by the conversion factor 1 gram over Avogadro's number times AMU. So this means it's just 1 over Avogadro's number grams. Okay? Let's do another example. So, okay. Actually, we have some practice problems, so we can do those later. So, how do we find the molar mass of a molecule or a formula unit? So, for example, like NaCl. How do we find the molar mass of NaCl? All we need to do is add all of the molar masses of the atoms that make up that compound together. Okay? And the electrons don't really impact the molar mass since electrons are too light to matter. Okay, so So look at your periodic table, and can someone tell me the molar mass of Fe? We'll just do this, okay? Can someone tell me the molar mass of this? Actually, let's just make it Cu. So, okay. So can someone type the molar mass of that compound in the chat? So molecular weight, it's also called molecular weight. By the way, I just want to make, okay, so just to you're close. You have to remember that the NO3 has a subscript underneath it. So we have 2 nitrates. So we have two of these. So can someone, how many copper atoms are there? All right, let's just do this step by step. So how many copper atoms are there? One, right? How many nitrogens are there? Great. And how many oxygens are there? 6. So when we sum this all together, what do we get? So look at your periodic table. Or if you don't have one, you can just use mine. So we need to sum this, and then this times 2, and then this times 6. So 63.5. So 63.5 plus 2 times 14 plus 6 times 16 equals 187.5. Okay. So this is the answer. Okay. So it's a little concerning. Wait, so everyone knows how to do this, right? Because I can't overstate how important this is. So how about this? So I'm going to do more examples, and I need every one of you to try your best to put the answers in the chat, okay? And then at the end of 10 minutes, I'll come back and how about this? At the end of 10 minutes, we can look at them, okay? So, and if you finish early, just take a break, okay? So let's do this. So, okay. So I'll come back at So how about we come back at 8:15 and just find the molar masses of these compounds. And if you finish early, just take a break, okay?